Hello, you lovely lot. I'm Teacher Jess, and welcome back to Geo Cafe. Joining us is Loki. Loki, say hi. Hey, so what I was hoping to do today, I would like to take a look over the 10 things that I, as a geography teacher, feel like students need to know, specifically about atmospheric science. It's going to start from the very basic concepts, and we're going to keep building on it to the more complicated concepts. And I added in one more little bonus fact. This bonus fact is actually the one fact that I think I and other geography teachers hate to teach. It's the one fact that is the most difficult to explain. But we'll see how I do when I get to the end of it, and we'll see if it makes sense. Okay, so let's get started. So, 10 facts that you need to know about atmospheric science. And the most important, is that the equator is hot. It's a very good place to start. It's the most fundamental thing that we need to understand about anything that happens in the atmosphere, any type of circulation. It all originates from the fact that the equator is hot. Okay, so the reason for this is because of the uneven distribution of sunlight across the Earth. Because of the shape of the Earth, we have more heating around the equator and less around the poles. So our first rule is that it's always hottest at the equator and it becomes colder as we move towards the poles. This map just shows you the distribution of heat across the Earth. You can see the red section around here by the equator, that's the warmest section. You can see that it slowly moves towards blue as it gets towards the poles. And all of this comes down to the shape of the Earth, our lovely little geoid, and how it receives energy from the sun. So there's three main reasons why the equator is hotter than the poles. One, you can say that the sun is shining more directly onto the equator, whilst towards your higher latitudes or your poles, it shines at an angle. The other reason is around the equator, it's lighting up a much smaller area of land, so the sunlight is more concentrated. But towards the poles, it's spread over a larger area because it's shining at an angle, which means that the heat is also more distributed. The other reason, what it actually comes down to, is the amount of atmosphere that it needs to travel through. So here by the equator, you can see very direct. It doesn't travel as far. And when it doesn't have to travel as far, you don't have as much sunlight being absorbed or reflected or scattered and lost back to space. But here towards the high latitudes or towards the poles, because it's coming in at an angle, it travels much further and more is then lost because of scattering, reflection, absorption, and all of those things. This is something worth understanding when we get to the atmospheric circulations, why we have the tricellular model, different ocean currents, tropical cyclones versus mid-latitude cyclones. All of those things come to the different heat distribution. My second fact is that the ocean is lazy. And what I mean by that is that the ocean is very slow to change in temperature. So the ocean and any other large body of water takes a very long time to heat up or cool down when you compare it to the land. Land, on the other hand, is a little bit hyperactive. You give a little bit of energy and it's suddenly very warm. You take away energy and suddenly it's very cold. So it all comes down to the different heat capacity of the different material. But in essence, the ocean is lazy. It doesn't want to change. And we see that effect on day to day and season to season. This just shows you Southern Africa in general. We can see that at this time, the land was really warm, 36 degrees there, 35 degrees there. But towards the coastline, we have 23, 23, 25. That's because the ocean doesn't really want to heat up during the day. So the land heats up and the ocean just stays mellow. Doesn't necessarily mean that the ocean is always cooler, because in nighttime the ocean can actually be warmer than inland. Here, okay, it's not really cooler than what we had before, but if we compare, that 23 used to be 36 and that 18 is 23. Over here, we've got a 5-degree change, and over here, we've got 13-degree difference versus 5-degree difference. So you can see anything along the ocean, it's lazy, it doesn't want to change. And that also goes from season to season. The ocean, for example, will be the warmest at the end of summer. So it takes an entire season for it to finally start warm up. So end of summer, early autumn, that's when it's the warmest. And then, of course, it will be the coldest at the end of winter or early spring. So this laziness of the ocean actually has a moderating effect on the local coastline. So it keeps it at a very mild temperature and very mild climate. During the day, we can have a lovely sea breeze coming in where the ocean feels cooler than the land and it brings that lovely breeze in. And at nighttime, we see it the other way around, where suddenly the land is cooler and in comparison, the sea is actually warmer. So you've got a change in the wind direction. And this difference in temperature is also the essence of what drives the monsoons. Because the ocean doesn't really want to change temperature and the land does, we see these type of seasonal weather phenomena and change in wind. Fact number 3, hot air rises and cold air sinks. Yes, again, it feels like something that is quite obvious, but it's a very fundamental part to understanding how the atmosphere circulates and all of the different events that happen. Warm air will expand. As it expands, it becomes less dense and it rises up. Cold air contracts. As it contracts, it becomes more dense and it sinks back down. This movement of air does cause a lot of our different circulations. I'll get into them in another minute. Here we have our warm air rising, we have our cold air sinking, and then what comes with that is different pressure at the surface of the earth. If we have warm, less dense air, that air will be rising up and it will relieve the weight off of the ground. So we'll have a lower pressure at the surface. If we have cold, dense, heavy air, that air will sink and will push onto the ground and will apply pressure at the surface. In the atmosphere, high pressure means dry. If we think about precipitation or any type of rainfall, what needs to happen if you look at your very basic little water cycle? You usually have the sun shining onto the ocean, and then you've got the heating, and then you've got the evaporation and the rising and the clouds and the works. Hopefully we've done the water cycle enough times to have this whole little process memorized. But one of the most important things that happens over here is the air rising. So we have to have the evaporation and we have to have that warm air rising with the moisture. And as it rises, it will cool and condense to form clouds. That is then where your precipitation comes from. It's not always just heating that causes the rising, but the air has to rise for some type of precipitation. What that means for high pressure is the opposite. My dog is protecting her. Okay, so what that means for high pressure is the opposite. If there's a high pressure, there's air sinking. So the air is blocked from rising and it can't condense and it can't form clouds, which means that high is dry. So wherever you see a high pressure system, it will prevent precipitation or rain from falling. And we see this on a global scale as well. Over here, we've got our equatorial lows. If you remember, the equator is hot. Hot air rises, and rising air is a low pressure. Now we've also learned that low pressure brings rain. That explains why all of this looks so green and lush. Over here, we have air sinking. We've got high pressure systems. And what that means is that rain is blocked off in this area. And that's why we have the deserts over there and over there. There is another little thing happening over here, but that is more related to the ocean currents. That's why some of these areas will still get rain, but you can see the general trend. You can see that wherever you have high pressure systems, you also have very dry conditions. Now we're going to jump up a few levels to the wandering ITCZ. So the ITCZ is an abbreviation for the Intertropical Convergence Zone. This usually happens over the equator, not exclusively over the equator, just in that area. So if we remember, the equator is hot, right? We learned that in fact number 1, which means hot air rises. And if hot air is rising, it leaves space for other air to come together and to converge at that place. You can almost think about it like a vacuum cleaner. If this air is being pulled up, it's suctioning the other air from the sides to come and merge in the middle. Where we have this happening, where we have that hot air rising and this wind from all directions converging to that hot area, we have our intertropical conversion zone. And the name is specific to happen between the tropics. That is because it actually migrates over the seasons. It doesn't just happen on the equator, it happens between the tropics. As the seasons change, the area with the most direct heating also changes. Let's take a look at this diagram, for example. If we see our Earth is tilted, this is how our seasons happen. We have sunlight coming in. Do you see which hemisphere is getting the most direct sunlight? Do you notice it's the southern hemisphere, which means that this latitude will be the one with the most heating. So this lovely little diagram that I had over here won't look like this. All of this will shift to the south. And with my majestic editing skills, I managed to make this map. Not the best, but it does the job. This part of the Earth is now getting all the heating. This is the part of the Earth where the hot air is rising and all of the air is converging to that line over there, which means that the ITCZ, the convergence zone, is around here. Then, in the other half of the year, where the northern hemisphere gets the most sunlight, the same thing happens in the northern hemisphere. Now, this is the part of the world the most heating. This is where the hot air rises. This is where it converges, and that is where the ITCZ occurs. The ITCZ is an important concept to know because it's almost like the equator of all things atmosphere. It's the 0 point, the starting point. When the ITCZ moves, many other atmospheric circulations and events move as well. Because the Earth isn't a perfect little round uniform bubble, it's made up of land and ocean and all of these other delightful things. The ITCZ actually isn't a straight line like what I had in my diagram. It's this little wibbly wobbly thing that is reformed because of our continents. And as the seasons go on and the ITCZ moves, other atmospheric systems move as well. One example that the South African students need to understand is how the mid-latitude cyclones move. In summer, the mid-latitude cyclones are very far south, so it doesn't reach South Africa. And in winter, as the ITCZ moves more north, the cyclones, the mid-latitude cyclones, also move north, and it brings with rain cold fronts. Okay, now we're going to start to get to the more technical stuff. This is where it starts to get complicated, so you're going to have to bear with me. I'm probably going to have to pull out a few diagrams, and my diagrams are always perfect quality. They're amazing diagrams. My next fact, I also refer to it as the first law of wind. So when my students get stuck on a question, I always remind them back to the first law of wind. And that is wind blows from a high to a low, always. So if in doubt, if we see a high pressure and a low pressure and we're trying to figure out where to go next, think about the wind. Wind blows from high to low. We refer to that as the pressure gradient force. Pressure gradient force is wind always blowing from a high pressure to a low pressure. And honestly, the idea of that is not so absurd. If you see a high pressure situation, you wouldn't want to be in it. You know, if something looks stressful, you would try to avoid it. So the air by the high pressure is trying to avoid that, and it moves towards the low pressure. To explain this, I want to try and use a diagram. The pressure gradient force works on the idea of gradient. Let's try and use a little diagram. Let's say we have a hill. When we describe the landscape of this hill, we can recognize that that is the high part and that is the low part, high and low. And in the same way, we have high pressure and low pressure. We have the high part of the hill and the low part of the hill. If we imagine that the wind is a ball, if the ball is on the top of the hill, it's going to roll down the hill and it will roll towards the low part. I'm trying to draw on a trackpad in Swell. I mean, it's amazing. No, I'm actually erasing the hill now. There we go. So the ball rolls from the high part of the hill to the low part of the hill. The same way the wind would blow from the high pressure to the low pressure. But how quickly the ball rolls depends on how steep the hill is. There, I've got it a bit more exaggerated now. If we look at these two little hills, the ball on the top hill, the first one, would look like it will roll slowly. Because it doesn't have a very steep hill, it would slowly make its way down to the low. Slow. There. And in this case, where we have a very steep hill, the ball will build up speed as it travels down, and the steeper the hill is, the faster the ball would roll down. It's perfect. I love it. Okay, so the ball would roll down quickly if it's on a steeper hill. And it's the same thing with the pressure gradient force. Where we have a very big difference between high and low pressure, the wind would blow very quickly. Where you have a small difference between high and low, the wind would blow slowly. And one of the ways that we can recognize this is with isobars. Isobars are almost like the contour lines of atmospheric pressure. Okay, we can kind of see it in this one. But over here where you can see a low pressure, here you can see a high pressure, there's the H, there's the L, there's the L. You see all of these lines around it. You see a whole bunch of other stuff as well, but you see the lines around the high and the low. In the same way that a contour line shows points of the same height, an isobar shows points of the same pressure. As the pressure increases over here, the isobars, they get higher and higher and higher, and over there they get lower and lower towards the low. So the same way that we could see if a slope is steep or gentle, we would see that if the contour lines are close together or far apart, we can see that with the isobars as well. Over here, that they're close together, which means that this is steep. Over here, it's far apart, which means the slope is gentle. So that means that this area where the lines are close together, the ball will be rolling the fastest. The slope is the steepest, so the wind blows the strongest. Here, where they're far apart, the slope is gentle, so the wind is more gentle. I hope this is making sense. I know we took a very big jump from the equator's heart to understanding isobars. Which brings us to another tricky topic to understand, and that is Coriolis force. So the thing to know about Coriolis force is that it is a bully. It is always trying to push something off of its course. If wind is trying to blow from one place to another, Coriolis force is there to push it off of its path. Coriolis force is always trying to push something off of its trajectory. And that something in this case is the wind. So if the wind is trying to blow from one point to another in the southern hemisphere, it will try to push it to the left. And it will always push towards the right in the northern hemisphere. Now, remember that things aren't always traveling in the same direction. So the left and right comes from which way the object is moving. If the object is moving that way, it's going to be pushed to its left. If it's going to go that way, it's moving to its right. So even though it looks like they're both going the same way, which in a sense they are, because Coriolis force is caused by the turning of the Earth, we always think of the left and the right from the perspective of the thing moving. If you fully understand pressure gradient force and the idea that Coriolis force is a bully, then I think we can move on to geostrophic flow. Geostrophic flow is what happens when the wind is stuck between these two forces. Pressure gradient force is trying to blow the wind from a high to a low, and then Coriolis force is trying to just move it to the left or the right. So Coriolis force is always just going to knock things off of its path. But sometimes these two forces reach a balance. That is when you have geostrophic flow. Now let's imagine that this is my high pressure. Ooh, I know, let's change this. We're going to make the high pressure blue because usually cold areas have high pressure. And I say usually because there is actually a exception to that. We'll get to that. Okay, and then we're going to make the low pressure warm because warm air rises and it makes a low pressure. Pressure gradient force would want to do its thing, and the wind would want to blow from the high pressure to the low. Let's make that purple. Pressure gradient force is going to be in purple, and it really wants to blow from the high pressure to the low pressure. But Coriolis is a bully. Which hemisphere should this be in? I'm going to go with southern, because South Africa, southern hemisphere. We're in the southern hemisphere, which means that Coriolis force will always push to the left. What color should we make that? Maybe orange? I'm going orange. There we go. Coriolis force always pushing to the left. So with our little arrow over here, the wind is trying to follow the pressure gradient force. It's trying to blow from the high to the low, but Coriolis force is going to push it to the left. Coriolis force would be blowing that way, right? Which means that the poor little wind that's trying to blow between these two forces is going to be tugged into both directions. So it's going to end up following this path. Does that make sense so far? At its new position, it still wants to follow the pressure gradient force. It still wants to move in that direction. But Coriolis force always pushes to the left of where that object is moving. So do we see that it's moving this way? Like that. So it's going to push to the left of that, if that makes sense. So it's going to push that way. It's pushing to the left of which way the thing is moving, which means that our little wind, once again, gets stuck between these two forces and ends up blowing that way between the two. Pressure gradient force still trying to do its thing. It's still trying to go from high to low. Coriolis force is still a bully. It's still just going to try and push it to the left. So the left is kind of like that. And then once again, the poor little wind is caught between the two forces and it needs to find a middle ground. Eventually, sometimes it happens that the pressure gradient force pulling that way is balanced with Coriolis force pulling this way. And that is when you have geostrophic flow. When there's a balance between the force that's trying to pull it to the low or push it towards the low and the force that's just being a bully and pushing it to the left, then it reaches a geostrophic flow or geostrophic wind. Hopefully we're starting to see that with these two forces, you have this weird curve in the wind. You see that it deflects to one side. We're going to build on that more as we get to our next fact. Cyclonic and anti-cyclonic. So cyclonic and anti-cyclonic relate to low pressure and high pressure. Regardless of what hemisphere you're in, wind will move around a low pressure in a cyclonic direction. It'll move around a high pressure in an anti-cyclonic direction. But which direction cyclonic and anti-cyclonic are does depend on the hemisphere. So just to show you where it's going to go, and then I'm going to use the diagram to try and explain it. In a northern hemisphere, cyclonic is anti-clockwise. You can see it goes that way. And anti-cyclonic is clockwise. In the southern hemisphere, cyclonic is clockwise and anti-cyclonic is anti-clockwise. Let's do a little diagram and see if it makes more sense. If we remember our pressure gradient force wants the wind to blow away from the high pressure. So let's just put in a few arrows. Yeah, that should be good enough. We've got a few arrows blowing away from the high pressure. And then we have Coriolis force. Coriolis force is a bully and it pushes everything to the left. Well, southern hemisphere to the left. If this is going to push to the left, so that's that way. I'm kind of trying to do it at like right angles, but it's tricky. So always to the left of the direction that it's moving in. So it wants to move that way, and that's to the left of this. And then of course the wind is going to be stuck between those two directions. So it's going to be stuck moving there, there. Let's neaten up this diagram a little bit because we have a lot of arrows going everywhere. I'm hoping that you're seeing it. I hope that you can see the arrows all pointing in an anti-clockwise direction. So that would be anti-cyclonic. Anti-cyclonic, anti-clockwise in the southern hemisphere. In the northern hemisphere, anti-cyclonic would be clockwise. A low pressure cell, cyclonic is clockwise in the southern hemisphere and anti-clockwise in the hemisphere. Okay, so I say that usually high pressure systems come from cold air. So cold air is dense, it's heavy and sinks. But sometimes high pressure systems can mean warm air. Don't panic, I will explain. Okay, it's a process called adiabatic heating. Basically, where you have air or other gases under pressure, those gases can warm up or would warm up even without needing to heat them. An example of this is aerosol tin. So like deodorant or I don't know, anything else that you might spray. So anything in a pressurized tin that you spray, if you feel it, it feels cold. And this is why. Because that sudden relief of pressure also drops the temperature. And in adiabatic heating, it works the other way. So we apply pressure to the atmosphere or to the air, and it warms up as it gets towards the surface of the earth. Before I have students panicking, saying, how are they going to remember which is which? Because usually where you have cold air, the air is dense and it sinks. So typically where you have a map in maybe winter or a cold area, you would also find a high pressure system. Then why do we sometimes see warm air with high pressure systems? It's which one comes first. If the air is hot, you can assume that it would rise and form a low pressure. If there is a high pressure, if the question or the information starts with there being a high pressure, then the air is heated. The reason why I put it that way, that the high pressure is there first, is because air doesn't always sink from being cold. There are a few times, like what we see over mountains, where air sinks because of things like topography. So in this case, the air is rising up to get over the mountain. We've got rain and all other things happening. And when it gets to the other side of the mountain, it will sink back down again. That sinking means that we have pressure there. That's not related to temperature. It didn't need to be cold for the air to start sinking. It was already sinking. When that happens, when there is a high pressure, regardless of the temperature, that's when it starts to warm. That is also why when we have our subtropical highs, it is warmer. Yes, where we have the polar high, it exists because it's cold and the air is sinking. But where we have the subtropical highs, where the air is sinking, it heats up with adiabatic heating. And that's why these deserts are so warm, despite the fact that they're so far from the equator. And I believe that those are our 10 facts, which brings us to our last fact, the bonus fact. Hey, this is not a fact that you critically need to know to excel in atmospheric science, but it's a fact that I hate teaching and other teachers hate teaching because it uses the worst possible words. So I just spent all of that time explaining to you that clockwise and cyclonic and low and high and all of those delightful things. And along comes these two concepts called backing and veering. And we hate these definitions because it describes a change in wind from clockwise to anti-clockwise. Where we usually cover backing and veering is when we look at mid-latitude cyclones. So something like this. Mid-latitude cyclone, it's a low pressure system, so it moves in a cyclonic direction. But as a cold front, like over here, passes over the point, the wind will start backing. And that usually confuses the students because that means it's moving anti-clockwise? No, it's actually still moving clockwise. This whole system is still moving clockwise. It's just that the appearance seems to have changed to an anti-clockwise direction. I'm going to explain this with one last diagram. Okay, so I've done a little diagram of a low pressure system. It's supposed to be a mid-latitude cyclone. And you can see over there, this is the cold front, and there's the person. So there's the person hearing on the news or the radio, the weather forecast, there's a cold front coming in with miserable weather, lots of rain, find your warm tops, find your umbrellas. As the cold front passes over, or as it starts arriving, do you notice which way the wind is blowing from? So let's kind of try to draw it from the person's perspective. Do you see how the arrows are pointing that way? That's the way the wind seems to blow. Then, sometime later, the cold front passes. I'm just moving it up so you can see the arrow. Can you see which way the wind seems to be blowing now? If we look over here. So remember, I did move it up a little bit. It was supposed to be there. So you can see that the wind is blowing like that. Okay, so let's add another arrow. Okay, now the wind feels like it's blowing from the north towards the south. And if we move it across a bit more, there we go. Notice which way the arrow is going now. There. It appears to be coming from the west, right? Notice how the arrows change directions. First it was coming from here, then from there. So where the wind felt like it was coming from moved like that. It moved in an anti-clockwise direction. That is what backing is. It's not that the wind itself is moving anti-clockwise. Let's bring our little cyclone back. The wind is still moving clockwise, but as it passes over, where the wind comes from feels like it's changing. That is what backing is. The point of origin feels like it's moving anti-clockwise. The wind itself it's a apparent shift in wind direction. So that was the most summed up that I can try to do backing and veering, and also my best efforts at summarizing what I think are the most important concepts to understand for atmospheric science. This is purely just based on the topics that I see my students struggle with. These are the things that they often need to go back to, need to remind themselves of. So if you have these 10 facts down, if you have these 10 points mastered, you understand them as concepts completely, you have a good foundation to excel in atmospheric science. Oh, you're welcome. Thank you very much for joining. I appreciate it. I hope you enjoyed that. I hope you learned something new, or maybe had a few questions answered. Otherwise, I hope that you have a lovely day, and then I'll see you again next time. Be good. Cheers. Bye.